Okay, so the next thing we want to do is picking up right here from linear function, constant rate of change, and we want to talk about what's called a piecewise linear function. This is really important. Another important building block for calculus is piecewise linear function, which means we're going to have more than one linear function, and we're going to piece them together. So we're talking about a function that has a constant rate of change, and then it has different constant rates over different x intervals. So for example, I can just make them an example here. So a car travels 63 miles per hour for 0.41 hours. And then 71 miles per hour for 1.29 hours. So is there a function for the total distance traveled by the car as a function of time? Does there exist a function where you could say this is how much time has gone by since the beginning, and this is the total distance traveled? And what would that function be like? So here's time since. Okay, how many is in a bunch here? Since starting. Time since starting at 63 miles per hour. And total distance traveled. So what's this going to look like?
It's going to be a line with positive slope for the first 0.41 hours, and then that slope is going to increase.
So this is how many hours right here? 0.41.
And that y value would be 63.
Would this y value be 63?
0.41 of 63.
Right, okay. And then the graph would look like what?
Get a little steeper.
So this represents going 63, and this represents going 71. So isn't this exactly what we're talking about? So to get a total distance traveled graph, okay, you would need two linear functions pieced together to get a total distance graph, right? And so look at this. How can we write the equation of this graph? You've got the tool now to do this the most efficiently. So you all know the linear function form that we've learned over the Friday and over the weekend, right? What is that? Y equals? New y?
No, it's new y.
Yeah, so, right. This is the new y, right? This is the new y?
Equals k, new x minus old x plus old y.
Okay. Change in x plus old y. Or m times, we can do x minus a plus b. That's a plus. Why is this very helpful for writing this piece of our function? You see that that's a really convenient way to do it. Why? Why is that much more convenient than y equals mx plus b? Oh, sorry, David. I didn't see your hand up.
X isn't starting from 0.
What's that?
The X doesn't start at 0.
Right, where does it start from? Yeah, so we'd be starting from here, right? So how can we build this? So how can we build that function? That piece of our function, meaning that line right there. How do we build this? What do we need? David, so you said that point. How does that point fit into creating this? Okay, so how does it fit into creating that?
So your M is 71.
Okay, she wants the M to be 71, right? M is 71, that's our rate of change.
And then was your X, your old X, so your A
A,
would be 0.41, right?
she wants 0.41 right there, is that right? And then B would be?
63 times 0.4.
Yeah, it would be that distance traveled at that point. That'd be that distance traveled. So we'd have the 0.41 would be here. And then 0.41 of 63 there for our distance traveled at that time. And then our 71.
What is that last part of the top equation saying?
Old y. Remember old y plus new y?
Yeah.
Or sorry, old y plus change in y? Yeah, that's old y. Okay, so also check out, here's another reason why y equals mx plus b isn't a good choice here. Because what is b? 0? For this part. Yeah, so it's kind of devoid of meaning. You see that? We could come up with a fictitious situation that gives that meaning, but in the actual situation that's going on here, the y-intercept of this graph doesn't have any meaning to the actual trip. Do you see that? So there's another reason why, besides being more convenient in this case for building a piecewise function, that y-intercept just doesn't have meaning. Or meaning connected to the actual situation. Like I said, we could make up some scenario of another car, right? But in terms of this particular car, that means nothing. Okay, so let's do so that was just kind of motivates this, show you how the form that you learned over the weekend and on Friday is the best form for building these piecewise functions. Okay. So this is the one we want to build. So we want to write a function f that has a rate of change of 2 over the interval -2, 1, and passes to the point -1, 1. So the first thing we want to do is we want to make sure we distinguish between an ordered pair, a point, and an interval. And how do you do that? Through the context of how it's given. All right. So they look exactly the same, but you have to use the context to figure out, is it talking about an interval or is it talking about a point? So this is talking about all x values from -2 to 1. This is the point xy, -1, 1. Same thing here. This is 1 is less than x is less than 5. And we want to connect that up with the first graph. Okay, so just look at this first piece. Can you write the linear form that we learned given this information? So given this information right here, in this first, write the linear form of the first piece of this function. Go, see if you can do it. Olivia, did you get it? Okay, so what was the form that we learned for a linear function? Y equals m times x minus a. So now we just have to apply that to the given information here. Elizabeth, did you get it? No. What do these things mean, right? So we did lots of homework problems on Friday so to really understand everything about this, what it means. So now we're just applying that. Dan, can you get it?
Well, there's a horizontal line, right? So, because,
Is that a horizontal line? Rate of change of 2? Is that a horizontal line?
oh no.
Corey,
I got y equals 2
2 times
x plus 1 plus 1
x minus negative 1 plus 1. Right? So this is starting value of x and starting value of y are an ordered pair, a, b, and m is our constant rate of change. M is the constant rate of change. Okay, so what we can do is we can call that f1. It's a function, right? Because it has an input x and it cranks out an output y. So we can call that f1. Okay, so that's f1. So what about f2? F2 in red. So f2 is the second piece, or the second linear piece. Who wants to give this a shot? Sharon. Negative 0.5.
Times x. Because it connects with the first interval, you have to use the point that was.
Okay, so now we have to think about this.
The first interval would end at x equals 1.
The first interval ends at x equals 1.
Therefore, you plug in x equals 1 in the first equation to find out the coordinates at which it ends, which is 1, 3. And then you take that point as your starting point for your second.
Yeah, exactly. So, Andrew, well said. So, we want it to connect. That means when we get to x equals 1, that will be whatever point we end at 1 will be the starting point of the second function, right? So that's the point we want to use. So the x coordinate of that point is 1. So here's the question. Do we have to calculate the y coordinate at that point? Or is there some other way we can represent it? Which f?
Of 1.
f1 of 1. Isn't that f1 of 1? You see? So especially when the numbers get complicated and we've got lots of pieces, this is a lot more convenient. Because what does that represent? That represents the y value of this one at the end of the interval when x equals 1. So we could find that. You could plug 1 into this, and you could get that y value. Or you can just, it's the same as that. Just represent it that way. Okay, any questions? So let's see what the graph looks like. Anybody have a question? Does it make sense? Okay, so there's the first one. That's that first graph, and we came up with the equation, what? F of 1 is? 2 times x minus 1. That's what we got, right? And then for the second one, we got that, right? So to make the one function that's both of those put together, here's what we do. You stack them on top of each other, and here's the first rule for x values in this interval. Oh, sorry. So for this interval here, from -2 to 1, notice in that interval we've got that first line, and we're specifying that interval here. And then from 1 to 5, this interval, we've got this line, and we're specifying the interval there. Okay, so your homework for Friday is, or Wednesday, is there's a new kind of chapter that you're going to read and do some reflections and answer some questions, and you're going to build one of these, okay? You're going to build one of these piecewise functions. See you Wednesday. No, just on paper.
So I saw